Okay, today we're going to be doing an example of solving a rational inequality. Again, a rational expression is a fraction where the numerator and the denominator are polynomials, and an inequality, of course, means we've got a greater than or less than sign. We want to solve this for x. Our solution is going to be an interval, so we're going to express it in interval notation. So our first step in these problems are to convert our original statement into this form where we've got p of x and q of x and some inequality here. It doesn't have to be greater than or equal to, just whatever this simplifies to, but we do want 0 on the other side, and we want to simplify our polynomials p of x and q of x as much as we can. So to get rid of this 1 and turn it into 0, we're going to subtract 1 from both sides, and we'll have this situation. Now we want to convert this to a single rational expression. So we're going to have to turn 1 into a fraction and find an LCD because we are subtracting two fractions. In this case, our LCD is x minus 3. And once we have the same denominator, we can subtract the numerators. I remove the 1's out front of the parentheses because 1 times anything is just itself, of course. So it gives us the situation. We've got a minus in front of this parenthesis we need to distribute through, so we get x minus 1 minus x plus 3 in our numerator, and combining like terms, that just gives us 2 because the x's cancel out. So here is our simplified rational expression. 2 over x minus 3 is greater than or equal to 0. So at this point we want to find our boundary points, and the boundary points are found by setting the numerator and the denominator equal to 0 and solving for x. In that case, our numerator is 2, so there's no way we can ever get our numerator to be 0, so we're going to just concentrate on our denominator, which is x minus 3 equals 0, and adding 3 to both sides we just get x equals 3. So our only boundary point for this problem is x equals 3. After you found all your boundary points, you want to test points between each boundary point and one that's higher than any of your boundary points and one point that's lower than any of your boundary points. So in this case, since we only have one boundary point, we choose one value to the left and one value to the right of 3. I always choose 0 if it's a possibility, so my point to the left, my test point to the left will be 0. The easiest test point to the right of my boundary point will be 4. So testing 0, just plug it in and I get 2 over 0 minus 3 is greater than or equal to 0. 2 over negative 3 is greater than or equal to 0, and whenever we have a fraction with a negative sign inside the numerator, the denominator, we can just pull it out to the side. So negative 2/3 is greater than or equal to 0. That is false. So the point 0 is not part of our solution set or our interval. So we know that every point to the left of that boundary point 3 is also not going to be a solution. Let's try 4. Plugging in 4, we get 2 over 4 minus 3, which is 2 over 1, and 2 over 1 is 2. And 2 is in fact greater than or equal to 0, so that's true. And every point to the right of our boundary point, the interval that contains 4, is going to be a solution to our rational inequality. So graph it on the number line, it always helps. I plot my boundary points in black. In this case I only have one, which is at 3. I tested 0, that's false, and I tested 4, which is true. So I know that every point on this side of 3, my boundary point, is going to be a solution to my inequality. We have to make sure that we do not include 3 in the solution set. It did have a greater than or equal to, so it might be tempting to include it because normally we put a bracket if it's greater than or equal to, but we realize that the boundary point is not going to be what we want because it will give us a 0 denominator which is undefined. So we want to throw out x equals 3, but every point to the right of 3 is going to give us a true statement. So the way we write our interval notation is parenthesis 3 comma infinity, And we can actually use Desmos or a graphing tool to check our work on that. So I'm going to graph our rational function and see what it looks like. Okay, here is the graph of f of x equals 2 over x minus 3. I'm just graphing this function. I'm not setting it equal to 0 or greater than or equal to 0. I just want to look at the curve, and I want to find the points on this curve that are greater than or equal to 0. So that would be the y values that are positive. And we can see that it's all of these numbers from 3 and on to infinity. We can see that there's a vertical asymptote here of x equals 3 and a horizontal asymptote of y equals 0. So this branch of the curve is always going to be positive. It goes up to positive infinity as x approaches 3 from the right side, and as x approaches infinity it's going to approach 0 from the positive direction. So we can see all of these values are always going to be positive, and that's the branch of the x values are from 3 to infinity, but not including 3 because that's our asymptote. Okay, that's all for today.